Okay, so here we have some examples where we're going to be simplifying, and the radicands are numbers. So there's no variables in here on these three problems. So that's why I called it Simplify Numeric Radicands. Okay, so I see the square root of 288. So maybe I'm thinking, oh, 288, that's 144 times 2. And then I know the square root of 144, it's 12. Now you can write, them separately, especially at the beginning maybe, but a lot of times we kind of skip that step. The square root of 144 is 12, so you get 12 times the square root of 2. That's the answer. But if you didn't know what 288 was, you could start breaking it down. 2, okay, that's going to be 144, and then you could say, okay, that's going to be 2 times 72, and that's going to be 8 times 9, and then that's going to be 2 times 4, and then that's going to be 3 times 3, and then I've got another 4. Okay, so you get a prime factorization of, let's see, 1, 2, 3, 4, 5 2's, and then there are 2 3's. I just write it out like this so I can circle them. And then for every pair on the inside, you get 1 on the outside. It's like they get to go out. Okay, but the other 2, it doesn't have a pair. It doesn't have a partner. So now the 3 gets to come out. And then you're going to have to multiply the 2 times 2 times 3, but that's 4 times 3, which is 12. So you get the same answer. It's just kind of a default. If you can't think of what the 288 is going to break into, or you don't see it, you could always go that route. So either way, I don't care which way you do it. They both are wonderful methods. Okay, so this next one's a little bit different. We'll do this one both ways as well. So you have the cubed root of 81. You might be thinking, now this is a cubed root, so you might be thinking 9 times 9, but that's not going to help us because that's a square root thing. We'll do that though in a second. It's 27 times 3, okay? And then you can split it up, the cubed root of 27 times the cubed root of 3. And that's the step I said we usually skip that step. But I want to point out, when you're writing the cubed root, you have to make sure you put that index in. If you don't, it's going to look like a square root, and I can't count it right. So make sure you put the index when you mean to. So the cubed root of 27 is 3. And then you have that little index there, the cubed root of 3. So each one of those 3's is important. They each serve a different purpose. Okay, but let's say you didn't know what 81 was. So you say, well, I know it's 9 times 9. And then I know 9 is, I didn't mean to write that. When you're doing a cubed root, you have to have a group of 3. Okay, so the index tells you how many to have in the group. So 9 breaks into 3 times 3, 3 times 3. So now what you have is you have the cubed root of 3 times 3 times 3 times 3. And then because this is a cubed root, square roots we had to have pairs, cubed roots we have to have a group of 3 to get 1 on the outside. So then you can write it like that, and you're going to get the same answer. It's a little unfortunate there were all those 3's in that problem, so hopefully it made some sense to you. Each 3 has a different purpose. Okay, well now we have the 4th root of 64. Okay, so you're like, I don't know what 64 is, but I know 64 is 8 times 8. And you get used to 8. 8 is just 3 2's. Okay, so that's what 64 is. It's all of those 2's. So I could say it's the 4th root. Again, I have to put that index. And there's 2 times 2 times 2 times 2 times 2 times 2. I think I got them. There's 6 of them. But I need a group of 4 because it's a 4th root. Okay? So I've got a group of 4 2's right there. I'm going to take that group out. And then what's left? These 2, they don't have enough to be a group of 4, so you just multiply them together. And then that's going to be the answer. Now you might be saying, well, I want to look at it the other way. Okay, well you can do that. It's the 4th root of 16 times 4. And then the fourth root of 16 is 2. And so you get the same answer. So some people are going to see it maybe this way, and some people are going to see it this way where we do the prime factorization. And like I said, I don't care which way. I think I've given you lists of perfect squares and perfect cubes. I don't think I have for perfect fourths. So 1 to the 4th power is 1. 2 to the 4th power is 16. 3 to the 4th power is 81. 4 to the 4th power, I want to say it's 256. I'm not going to know very many of these. All right, 4 to the 4th power. Yeah, 256. 256. And 5 to the 4th power is 625. Now, you can have larger numbers, but that's probably all I'm going to remember off the top of my head. Then you have to use a calculator to maybe break them down or figure them out. You can always use those prime factorizations, which is really helpful. Okay.